Hello and welcome to an introduction to partial derivatives. Prior to beginning with partial derivatives, I want you to think about what the derivative of a function of only one variable means, as well as the challenges this could make for derivative of a function of more than one variable. As you go through this video, you are encouraged to pause and attempt the problems and exercise yourself, and then afterwards watch them and compare your answer. So let's begin. So first question is, what does the derivative of the function f of x equals 3x squared at x equals 1 represent? The answer is it represents the slope of a tangent line. And so, as you may remember, a tangent line intersects the curve at exactly one point. Now, let's consider a function of the form f of x equals 3x squared plus y squared. You may remember that this function is what's called a paraboloid, or in other words, a three-dimensional surface where if you slice it in any direction from the top, it looks like a parabola. Now the issue here is that for one point, there actually are infinitely many tangent lines, because instead of a tangent line to a point for a surface, we end up with a tangent plane. So this is our issue with functions of more than one variable, is that we can approach a point from many different directions. Technically an infinite number, although you can think of it as from any angle, almost like if I take a point in the world, I can approach it from east, west, north, south, or any combination. Because in essence, a surface you can think of as being similar to the way the world is with a map. Now, because we can approach a point from many directions, we have to split up derivatives. Now, here we have functions that are z is a function of x and y. So what we end up doing with derivatives is we split derivatives as approaching from the x direction or approaching from the y direction. With functions of more than one variable, we have this idea of partial derivatives, meaning we're taking the derivative of part of the function because the derivative of the entire function creates a confusing definition. There are two main types of this. We have partial derivatives with respect to x, and we have partial derivatives with respect to y. The symbol for this is kind of a weird D. So if we call this symbol right here E, even though really it looks more like a backwards 6, but still we call it E. So partial derivative with respect to x, this is pronounced df dx. And what this is we are going to go parallel to the x-axis. So only x will be switching, and we're taking a slice where y is a set number. So this is kind of the tangent line if we look at z versus x. On the other hand, the partial derivative with respect to y is df dy, and this is where we set x equal to a fixed number, and we look at the function of z versus y, and we look at a tangent line for that. Before moving on to derivatives of functions of more than one variable, I want to review calculating derivatives of functions of a single variable. So two quick review problems. Take the derivative of 7x and then take the derivative of 9x squared. For the derivative of 7x, the derivative of x is 1. And if we have a number multiplying, we just take the number multiplying times the derivative. So this is 7 times 1, which is just 7. The next one, the derivative of sine of x is cosine of x. And if you have a number multiplying, the number multiplying just stays there. So the derivative of 9 sine x is 9 times cosine x. Now we consider how to take derivatives of a function of more than one variable. To do this, we treat the variable not involved in the derivative as a constant, meaning as a number. This was similar to on the graph, where the slice that we were using had one variable as a number and we were taking the tangent line in the direction of the other variable. For derivatives, we're not going to specify what number the other variable is. However, we act like it's a number. And as a reminder, if I have, say, 2 to the third, that's 8. So a number to the third remains a number, and it still is treated that way on a partial derivative. So let's consider how to take partial derivatives of the function f of x comma y is equal to y cubed e to the x to the fourth minus x squared times sine of 5y minus 1. Taking the partial derivative with respect to x df dx, we start out by looking at the first term, y cubed e to the x to the fourth. Because this is a partial with respect to x, y is considered a number, so we can consider y cubed to be just a number to the third, and that's just going to stay there as we take the derivative. On the other hand, the derivative of e to the x to the fourth, the outer function is e raised to a variable power, whose derivative is itself. Then the inner function is x to the fourth, whose derivative is 4x cubed. So by the chain rule, the derivative of this first part, e to the x to the fourth, its derivative is e to the x to the fourth, derivative of the outer, times 4x cubed, derivative of the inner function. The y to the third just remains out front since it is a number. It is considered to be a number when we take a partial derivative with respect to x, and so nothing is done with it. Next, we look at x squared times sine of 5y minus 1. Again, because we are taking a partial derivative with respect to x, y is considered to be a number. Now, sine of a number is still a number. So, when we take the partial derivative of x squared sine of 5y minus 1, the only thing we're actually taking a derivative of is x squared. And the derivative of x squared is 2x. This then gets multiplied by sine of 5y minus 1, as the entire part of sine of 5y minus 1, this is entirely a number, and a number multiplied and taken derivative remains there. Now let's take a look at the partial derivative of this function with respect to y. For the first part, now when we take a partial derivative with respect to y, all x's are treated as numbers. So if x is a number, then x to the fourth is still a number, and e to a number is still a number, so the entire e to the x to the fourth is a number. So taking the derivative of y to the third e to the x to the fourth, we are just taking the derivative of y to the third, and we are leaving e to the x to the fourth as a number. The derivative of y to the third is 3y squared, and then we multiply by the number e to the x to the fourth. For the next part, since x is being treated as a number, x squared is also a number. So we are only taking the derivative of sine of 5y minus 1. The derivative of sine is cosine, which covers the derivative of the outer function. The derivative of 5y minus 1 is 5. So the derivative of the second part is x squared, which is just a number and remains there, times, times it should be positive cosine of 5y minus 1 times 5. So again, in taking partial derivatives, the variable not involved is treated as just a number, and the variable as well as any items involving that variable just remain there. The other variable, we take derivatives as normal, and that is how we do partial derivatives. Similar to how we could evaluate a derivative at a single number to find the slope of a tangent line, we can do similar with partial derivatives to find the slope of a tangent line along a specific angle of approach. Now, similar to how it was awkward to do dy dx of a number, and so we used f prime, there's a similar notation for partial derivatives. However, the notation of prime does not work since now there's more than one type of derivative we have to consider. So instead, we use the notation a subscript of x to indicate df dx and a subscript of y to indicate df dy. We can then use this notation calculate a partial derivative and plug in values for x and y and find the number at that point. So let's consider the function f of xy is equal to 5x squared y plus y squared x squared. So for the partial with respect to x, we first of all take the partial derivative. So the derivative of x squared is 2x times 5 is 10x, and y is just a number when we're taking the partial derivative with respect to x. So the first part of the partial derivative is 10xy. For the second part, y squared is just a number, so being multiplied, it just stays there. Derivative of x squared is 2x. So this is our partial derivative. Now, because we are calculating f sub x of 4, 3, meaning the partial derivative with respect to x evaluated at the point 4, 3, we plug in 4 for x and 3 for y. We can then do this, so we now have 10 times 4 times 3 plus 3 squared times 2 times 4, and inserting this into a calculator gives us a value of 192. So that's the answer for the partial derivative of x at the point 4, 3. The process for y is similar. We first of all take the partial derivative with respect to y, where partial derivative of y with respect to itself is 1, x squared is considered a number, and 5 is considered a number. So for the first part, it's just 5x squared times 1, which is 5x squared. For the second part, the derivative of y squared with respect to y is 2y, and x squared is considered a number. So the derivative of the second part is 2y times x squared. Next, we put 4 in for x and 3 in for y, and then we plug the result into a calculator, giving a value of 176. So the partial derivative with respect to y of the function at 4, 3 is 176.